Yeah, let's get started. Here's the land acknowledgement. And as I said, we all start with some AI news. So I'm sure most of you have heard OpenAI released Sora 2, which is basically one of the best video generation platforms that you could see nowadays. You can generate like whole episodes of South Park and stuff. So that's really cool. And then also, I mentioned this last time, but here's the specific like paper you can look up. It's the NVIDIA physics simulation. They released something called like offset geometric contact. And as you can see, it's one of the most realistic simulations ever created. It can simulate like cloth and all this fancy stuff. So yeah, I mean, AI is the place to be, and advancements are happening literally every week. And of course, to promote UTMIST, there's always a machine learning fundamentals every Saturday from 1 to 3, which will provide you with amazing background. There are paper readings, AI is about reading papers from 3 to 6 Saturday. And once again, keep an eye out for the machine learning tournaments, reinforcement learning tournament as well, happening this reading week. Very good chance to, work on an actual reinforcement learning problem. And yeah, hopefully this course serves as a little bit of the baselines for that. Brief recap of last week. Recall, what makes reinforcement learning different. You have to maximize reward signal. Feedback is delayed. The actions on agent affect the environment, and data is sequential. This is the goal of reinforcement learning, to maximize the expected return, right? Everyone remembers this. There's a definition of a MDP, a Markov decision process. Yeah, this is it. You have the states, the actions, the transition function, and the reward function. And always don't forget the discount factor. You'll see a lot of this again today, so hopefully you guys all understand it. The policy is what makes lets the agent make decisions, makes the agent, you get a state, it tells the agent what action to take in the state. And this was something very important. I hope you guys still remember the state value function. It's how good a particular state is. It's where if you start in this state and you follow a policy, what is the expected return you'll get? Accounting for all the randomness and everything that will happen later. All future rewards are incorporated into this one number. Okay, once again, these are very important concepts, so please, make sure to know them. Okay, let's get on to today. We have so many things to cover. I'll try to give you guys a break, but we might not have one. So yeah, hopefully you guys aren't too tired. So if you recall last week, there was this, right? The state value function V of S, but I don't know if any of you remember the Q. There was a Q as well, Q of SA. It was called the state action value function. And this is another value function that is critically important in reinforcement learning. I hope you guys also understand this. So we'll spend the first section going over this just because of how important it is. It's very similar to a value function, but it's kind of different, okay? So the value function V, from now on when I say value function, I'll say V, okay? Or when I say value function, I mean V, right? V is how good a state is, accounting for all future rewards and randomness, everything. However, Q is how good, it's also a number, how good or bad a particular state and action is. Okay, so you can see it's defined as the expected return starting in this state, right? S, taking an action A, okay, some action in a state, and following policy pi. And you can see it's very similar sort of to the V definition, except it's conditioned on the action as well. It's not just the state. All right. So, what does this mean? Just like the value function, this encapsulates the future, right? The Q function takes into account all future rewards and randomness, but this time you start with a state and action, right? Just like the value function, I repeated this like 1,000 times last week. It depends on the policy and the transition dynamics, right? And the only difference is that V is for one state, but Q is for an action associated with that state. So let's see what that means really quick. So let's say you have this some environment. Okay, this is just, let's say, a grid, right? You have a grid world, and there's just some grid in that grid world. Okay, there's 4 valid actions per state: up, down, left, and right. And for this particular state, the policy is this thing over here. Okay. Now take the state below. So you guys are familiar with the V, right? So one state has a value, right? Let's say the value of this state is 10. That means this 10 is the expected return starting this state and going with the policy. Let me ask you, how many Q values are in this state? So if you have 4 actions, okay, and you have one state. So actually, there will be 4 Q values for this state. Does everyone understand that, right? You have a state that, and so you have a state and an action. You have 4 actions. You need a number for each of those actions telling you how good each action is. Okay, so that's just a Q, right? It's how good every state and action is, and V is how good each state is. Now, you might, some eagle-eyed viewers out there might notice that, these values aren't random. So what are they? If you notice, actually, if you weight each Q value by the probability of that action, its corresponding action. So here, this goes up with 10%. So you have 20 times 0.1, etc. It actually equals 10. So actually, mathematically, we say that for a particular state, the V, the value, is equal to the expected value of the Q function. Okay, I mean, this makes sense, right? How good the states over, and I don't want to get, so in this lecture, there will be a lot of equations, but instead of getting lost in the numbers and the sigmas and everything, just think about intuition, okay? I want you guys to think about intuitively what it means. So, I mean, intuitively, this makes sense, right? How good the state overall is, aka V, is equal to how good, each action is, weighted by its probability of occurring, right? I hope this sort of makes intuitive sense. And this is just a mathematical way of describing it. So this is just V in terms of Q. I hope this concept makes sense. Okay, if there are any questions, feel free to raise your hand. Okay, let's try this. Let's try this thing. So let's say you have this environment. You have these states here. You have a bunch of Q values right here. So these are terminal states, right? So the green is you get +1 return reward, and red is you get -1. So let me ask you, how many valid actions are there per state here? 4, right? Yeah, perfect. Okay. Now, what is the value, V, of this highlighted state? It's a little bit of a trick question. You don't know the policy, so you actually don't know. Okay, just, trying to get you thinking along the lines of what you need to calculate V and the relationship between V and Q. Okay, so yeah, hopefully everyone can sort of see what the Q function is. It's very similar to V, encapsulates all future rewards and returns and randomness, but you need a state in action. So it's still a number. And you can see, so let's say you take this state, right? This action, the up action has a value of 0.4. That means it's better than the down action with a value of 0.2. Okay? Okay, now we're getting into one of the more confusing parts of the course. Hopefully people can keep up. Yeah, last year I didn't do this well, so it was really confusing. This I revamped the slides. So hopefully my efforts pay off here. Before I do this though, who has heard of dynamic programming before? Yeah, okay. Like people have done it in class, implemented. Okay, that's fine. That's fine. So let's just quickly talk about dynamic programming. Basically, it's a method of solving complex problems by breaking them down to subproblems. Okay, you break down a big problem into little problems. You solve them individually, so these subproblems. You combine them into one big solution, and that will be like the final solution to the big hard problem. And this is not just a reinforcement learning term. I don't want you to think this is only reinforcement learning. It's a very, very common tool in all of computer science. So any of you CS majors out there, you'll like 100% chance you'll do this in the future. But so you can get a little bit of a head start now. General example, right? As I said, it applies to all areas of computer science and math, right? Fibonacci sequence. If you want to find the fourth Fibonacci number, right? It's equal to the second Fibonacci number plus the third one, right? And it's easier to find the second Fibonacci number than the fourth one. So you can first find these solutions to these simpler problems, i.e. F2 and F3, and combine them to get F4, right? It's the idea of using sort of existing knowledge, and you can combine them to get like a more complex solution to a harder question. So where does this apply in RL? Okay, let's see here. So let's say, okay, we're trying to estimate the value V of this state here, okay? You're trying to know the value, and I think hopefully this is exciting. We're actually getting to how to find the magical value function, right? You don't know the value of this state, right? But you know the value of these two next states, okay? The value of 40 and 20, okay? Let's say in this state, the policy is you take action A with 100% probability. So deterministic policy, right? Once you take action A, you get +5 reward, but you have a 25% chance. This is the transition probability, right, from the MDP. You have a 25% chance of going to state 40, or rather a state with value 40, and a 75% chance of going to state with value 20. Okay. Now, and of course, the discount factor, and don't forget the discount factor in MDPs is 0.9. So how would you find the value of this question mark state? What do we do here? Okay, so we just say, okay, so let's start in this inner bracket here, right? You sort of average the value of the future states, right? You multiply 40 by 0.25, right? You multiply 20 by 0.75. That's like the sort of average value of the future states you can reach from this state. Does that make sense while we're doing this, right? And you have to weight them by the probability of going to these states, right? You multiply by 0.9. What is 0.9? 0.9 is the discount factor. Because remember, we don't care as much about future returns and values as the current reward. So I have to multiply it by 0.9 for one step. If this was 2 steps, you do 0.9 squared, but this is 1 step. So multiply by 0.9, which is a discount factor. And of course, you add 5, right? Because you get some value, you get some reward for taking this particular action A in this state. So the value of this state is 27.5. Does this make sense to everyone? What we just did? And can you guys all see like why this is dynamic programming, quote unquote? Right? We're using known knowledge or the value of the future states, and of course the discount factor, the transition probabilities, and the reward to get the value of this unknown state. Right? Sort of putting a puzzle together. Okay, I hope this example makes sense. Yeah, go ahead. No. So 25 and 75 are the transition probabilities, right? The policy is the action that the agent takes in this state. And I said the policy is you take action A with 100% probability in this state. These 25 and 75 are the probability. So after you take the action, there's a 25% chance the environment sends you to this bottom state, a 75% chance the environment sends you to the top state. It's kind of like the wind almost, like there's some randomness in the environment. Okay. And this is dynamic programming, as I said. Now let's go a bit more complex here. Okay. Let's say now instead of taking one action with 100% probability, a deterministic policy in this state, let's say we have a stochastic policy. All right. Once again, what does that mean? Right? There's a chance, right? So let's say in this state, you take action A1 with 40% probability, you take action A2 with 60% probability. After you take action A1, you get +5 reward, and once again, like before, there's a chance of you going to here, there's a chance of you going to here, right? 25 and 75. However, if you take action A2, there's a 100% chance you'll go to this state with value 10. Okay, so here we have both a stochastic policy and stochastic dynamics. Oh, everyone sees that. I mean, it seems more complicated, but it's the same as before. Now, this equation seems hard, but let's break it down, right? So what you have here is 0.6 is the probability of taking this action, and okay, so maybe I should have written this equation better. So if you can imagine a line dividing these two terms, right? This term is, first of all, you have to weight this by the probability of taking this action A1, right, which is 0.4, 40%. And the equation is the same as before, 5 plus the discount factor times the average value, 0.25 times 40 plus 0.75 times 20, the average value of the future states, right? But this time, you can notice this is the same as the last side, right? 5 plus everything here. But you multiply by 0.4 because you have to weight it by the probability of taking that action. Before, the action was 100%, so you didn't need to care about the randomness, right? But here, there's only a 40% chance you'll take that action. So you have to multiply by that. And this term here, you consider the other action, right? 0.6, which is the probability of taking this other action. You have to add by the reward. So you get reward minus 10 here. So you take minus 10 plus, once again, 0.9 discount factor times the value of this next state. Does everyone see? Yeah, go ahead.
Yeah, so this would be the V, right?
Yes, this would be the value value of this state.
Right. So to compute the value, we don't necessarily need the policy, but for Q, we need the policy.
No. For value, you do need the policy here, right? Because you need the probability, right? If you didn't know 0.4 and 0.6 here, you wouldn't know what to multiply these things by.
So are the 0.4 and 0.6 the policy?
Yes, there's a 0.4% chance of taking action A1 in this environment, in this state, sorry. 0.6 chance of taking action A2. And taking actions A1, A2 will send you to different paths with its own reward and transition dynamics. Is this clear? Yeah, go ahead. No, so okay, so they could be. Actually, no, they couldn't be. But yeah, so these are just the values of some arbitrary other states, right? Okay, I should have added the ellipses here, but assume this tree branches out like more, right? This is just one snapshot of a particular state and its transitions. This state might have its own like transitions and everything. I'm just saying that if you have a state and you know the values of its next state, you know the discount factor, you know the transition probabilities, you know the reward, and you know its policy, you can calculate the value of this state by using your known information, right? These next state estimates. Make sense? Yeah, go ahead.
State. Is there one map?
What do you mean by go?
Side to side. Is
Mhm.
Math of current state to
Well, so we're saying if we know the value of the current state, can we estimate the value of the future states? No, I don't think you can because the value is a summary of everything that's happened in the future, right? So this state is the future of this state, and this state, you already know the summary of the future from this state. You get it? Like 40 is how good this state is in the future. So you're sort of back propagating. I don't like to use that word, but you're sort of back propagating this information to the past, right? Yeah. Go ahead.
And how would this work? There was some sort of cyclicity.
Some sort of cycle. Yeah, I mean, it could work. You would reference itself. Yeah. Oh, yeah, that's a good point. I should have included an example of a cycle. There you can just set up the equation, but like
Because if from this state we go to 40, and then at some point 40 might take us back to this state, then it sort of depends on itself.
right. So you only care about for our purposes, you only care about the one step in the future, right? So if you know the value one step in the future, you're good, right? But let's say this state A1 doesn't take you to 40 and 20, it loops back in on itself. Then like let's say A1 takes you back to this state. Then you would have to that's still possible. It's just you write the equation that way, but you might not be able to solve it. But using other methods, like if you have like a system, like if this is a whole system, you'd have this value being part of like another equation. So you can have a system of equations, you can solve it that way. In practice, if there's a cycle, you would probably solve it using some other algorithm that I'll talk about later. But yeah, you could have cycles. So my point is cycles can work. We won't cover them right now, but yeah, cycles can work. Yeah.
How value just go back all the way.
Yeah, that's okay. You're onto something there. Let's return to that. Okay, so that's the example. So what did the examples tell us, right? In order to estimate the value of the unknown state, you need the value estimates of the states from the unknown one, reachable from the unknown one. You only care about the states that are reachable. Okay. The policy, the probability of taking action, the transition dynamics, the reward, and the discount factor, right? This is everything we needed to calculate it. If the policy was deterministic, 100% one action, then I mean, we still need to know that, but like, so if it was deterministic, this value would just become 1, right? So it's fine. If the dynamics were deterministic, as they are in this case, this example, you can notice this is just 1 here, right? Here you have to account for 25 and 75, but here you have to put 1. Make sense? Okay, great. So now we want a sort of mathematical expression for the examples we did above, right? We want to relate the value of the current state to the value of its successor states. This can be done via something called the Bellman equations, and these are fundamental in reinforcement learning and dynamic programming. Yeah. So it's basically saying the value of the current state is equal to the reward received. Okay, there's a typo here. Received plus the values of the subsequent states, of course, weighted by the policy, considering the policy, the dynamics, and the discount factor. And this helps agent make long-term decisions. Why? Because if an agent knows that its next state, this next state is like, let's say 40 versus 10, right? It can have an idea of the value of the current state, right? This state is somewhere between 40 and 10, right? So how good this state is. So yeah, I hope you guys can see now a little bit about why like value functions account for all future randomness, right? Because so this 40, 20, and 10 already accounts, assume this is given to us, it already accounts for all future randomness, and you sort of update it backwards. So this state in the quote unquote past knows about the future returns. Okay, now here's some math, but it's just doing what we just did, okay? So don't, okay. So this is, imagine this, so this is what happened last year. I flashed this equation on screen and just assumed everyone understood. Okay, so hopefully this way makes it more clear. This equation is the Bellman equation for V. But you can notice it's exactly what we did just now, right? You have the policy, you account for the probabilities of the actions in each in the state, right? Remember, this was the 0.4 and 0.6. You have the dynamics, 25 and 75, 0.25, 0.75. You just do that, right? You account for that. And you take the reward plus the discount factor times the value of the next state. So, yeah, so let's here. So you multiply by the probabilities of actions, right? Account for the randomness of the policy. Here, this whole term here is the probabilities of the next states. You account for the transition dynamics, okay? And this is the current state value is equal to the reward obtained plus the values of next states, where S prime, so this prime notation, this apostrophe means next, okay, from now on. So S prime is next states, A prime is next actions, right? So does everyone see how this is exactly the same as what we just did? Right, this equation is just saying we take the values of the future states, discount them, add up the reward, right? And you multiply each of these numbers by how likely it is under the current policy and under the current transitions, right? These summations, these sigmas, are to account for the randomness of the policy and the dynamics. I hope this makes more sense. If this doesn't, feel free to revisit those examples. And there'll be some more later. And this is a key point, okay? You can account for randomness by averaging, right? These summations are like weighted averages. You can think of them as averaging, right? Does this make sense around? Like if something's really random, but you keep doing it a lot, the average will be the result. So if you flip a coin, right? If you flip it like twice or 10 times, maybe the distribution of heads and tails is not 50-50. You might get 7 heads, 3 tails. But if you do it 1,000 times, right, you'll get 50-50 pretty much. And this is what we're trying to do here, right? The policy is stochastic. The dynamics are stochastic. They're random. So we take the weighted average, the weighted sum, according to the probabilities of the policy and dynamics. I hope that makes sense. And this is just what we are doing there, right? Let's assume the white circles. This is like diagrammatically what is required. You start at the current state, right? You take some action, you get some reward, and these are the next state. So this is what's sort of required, like a tree diagram, what's required to calculate the value for this state according to the Bellman equation. Does that make sense? All right. This is just, yeah. Okay. Time for the Q function. Let's say you're trying to estimate the value QSA. Remember, this is a state and action, okay? You don't know the value of this state and action, but let's say you know the values of other states and actions. All right, let's say there are 2 actions per state, left and right, and you're trying to calculate the value of the right action in state A. QA question mark, all right? The value of the right action in state A. You know the policies in each of these states. You know what the successor states are, B and C, and you know that the value of the left action in state B is 2, the value of the right action in state B is 4, etc. So these are the Q values of the actions in state B and C. Does it make sense to everyone? And once again, of course, this is the reward, right? If you take the right action in state A, you get +5 reward. If you take the left action in state A, you get +10 reward. And these are the dynamics. Yeah.
So,
yes, but now it's the Q, right? Because there's 2 numbers now per state for 2 actions. So this is the Q. If you want the V, so how would you calculate the value of this state? Exactly. So everyone gets the difference, right, between Q and V. So, but these are the Q now, because there's 2 numbers per state. Okay. Okay. So let's break this down, right? So let's just do what we did just now. The value in state B is 2 times 80% and 4 times 20%, 2.4. The value in state C is 5.8. You just calculate the same way. Okay. Now you can just do what we did just now. You take reward plus the value of next states, right? Because you have to multiply by the transition probabilities, right? Because once again, there's some randomness here. You weight it by how likely each next state is. So you multiply 0.25 by 2.4 and 0.75 by 5.8. Does that make sense, right? You first calculate the value, right? And then you weight it by the probabilities. Make sense? Yeah. But don't forget the discount factor, right? Because once again, this is just to sort of train you guys thinking about this. You can't forget that we have to weight future returns lower. Okay. So let me ask you this: Are we done here? Actually, let me not ask you this. We're running out of time. We're done here, right? You might notice that I have this policy in state A. You know, it's 99%. There's only a 1% chance of going to the right in state A. That's pretty low percent. Also, I gave you some information like you get plus 10 reward when taking left action. But actually, it doesn't matter. You don't care about the policy in state A. Why is that? Because we already, in the definition of Q, we already specified which action we want the value of, we care about. We don't care about the left action in state A. There's no more randomness in the action in state A because we already specified which action we want to work with. Before with the value, recall with the value, we didn't specify which action to take. So we have to account for each action in the state. But here, we only care about the right action. We want the value of this, assuming we have already taken the right action. So yes, there's only a 1% chance of taking the right action, but assume that we have already taken it. We have already executed. However unlikely that is, what is the value of this action? Does everyone understand why we don't care about the other states? This is accounting for the fact we have already taken this action. We don't care. We don't care about this. So yeah, so that's it, right? The Q value is 9.46 because it is the reward plus the discount factor times the transition probabilities times the values of the next states, right? And once again, the values of the next states are weighted by the policy in the next states because there's only a 20% chance we get a value of 4 at the next state and a 80% chance we get a value of 2. So even though we don't have to account for the randomness of the policy in the current state, we have to account for the randomness of the policy in the next state, right? Because we haven't specified which action to take there. We have to account for the possible actions you can take there to calculate the value of the right action in state A. Makes sense? And this is the state action Bellman equation, i.e. Q in terms of Q. All right? Once again, it's exactly what we did just now. You take the dynamics, you account for the randomness in the dynamics, assuming you have already picked an action, right? Once again, A is here, you have already picked an action. You account for the randomness in the dynamics, you do the reward plus the discount factor, but as I said, you have to account for the randomness of the actions in the next states, right? Because this is Q of S prime and A prime, the next states and actions. They're gonna see that. Unlike the Q function, unlike the Bellman equation for the V function, sorry, there was no more like summation here. If you guys recall, there was a summation over the policy here. We don't care about that anymore because we already picked the action in the current state. The summation over the policy has been now moved to the inside, right? To the next states. Yeah, so this is what I just said, right? You have to account for the transition. So give me a sec. You have to account for the probabilities of the actions in the next states. And the value is the reward plus the discounted values of the next states. Yeah, go ahead.
That then we can calculate the value of the current state and then compare like.
So I mean that's just how the Q function is defined, right? Q of SA assumes you have picked an action. Yeah. Yeah. So Q, okay, so you're asking why is Q useful? It is extremely useful, much more than V actually. But we'll cover that next week. We'll get into why. But yeah, it is very important that you understand what the Q function is and what it implies. Both actually, Q and V. But Q is much more useful in practice than V. We'll see why. We'll see why.
So in this equation here, the summation over R is the transition probability.
It's
It's not the reward.
So R is part of the transition, right? Part of the environment. This is the summation over the environment, right? R is part of it. The environment gives you the reward, right?
So we're doing 0.75 times plus 0.25 times. That's this term, right?
Yes. So the probability of the next states is 0. So the probability of B is 0.25. The probability of C is 0.75. Yeah.
So here we have R equals 1 and R equals 2. Get two possible values for R.
No, S prime equals B or C. R is 5 plus 5.
And for
There's the probability of the next states, not the next rewards, the next states. You obtain a reward of 5 with 100% probability in this state after executing the right action. If this was a random reward thing, then you'd have then you need another like layer of, you need two summations. But here reward is always, deterministic. Actually, in most environments I've ever worked with, reward is deterministic. But you include it here, just in case. And this is the Q value Bellman equation diagram. It's really similar to the V, but notice before for V, you started with a state, a white circle. But here you start with a black circle because you've already picked a state in action. You start with an action. You go to the next state. You see what actions are available at these next states, and you use this to calculate the value, the QSA. Does that make sense? So yeah, it's a little bit different than V, right? Because V was white circle, black dot, white circle. Here's black dot, white circle, black dot. Okay. And yeah, I mean, this is just comparing the two. Notice where the randomness occurs, right? For V, we don't specify the action, so the randomness of the current policy needs to be taken account of. So there's a summation out here. For Q, we consider the action already. We already picked the action, so this disappears. But we need to, specify, we need to take account of the randomness of the next state's policy.
the actions.
Yeah, in the next state. And notice this Bellman equation, actually, let me just go to the next slide. Whatever. Yeah. So recall the setting, right? This was for the Q, right? This was what we did for the Q, right? We first averaged the value in the states B and C to go from Q to V, right? Because 2.4 and 5.8 are the V in B and C. Is that clear to everyone? It's just the average. So yeah, these values are the V. So actually what you can do, right? So once again, just repeating, remind you again the relation between V and Q. What you can do is take the Q Bellman equation, right? And you realize that actually this term here is actually just the value of the next states because it's just averaging over the action. Notice how similar this part of the equation is to here, right? So actually, you can just sort of rewrite it this way. So before we were rewriting Q in terms of Q and V in terms of V, but we don't have to do that. We can rewrite Q in terms of V and V in terms of Q. All right, this equation is just a rewriting of what we've seen before, right? I hope this is clear to everyone. This is valid, it's correct, but I've never seen this before. This is actually like kind of common, like you see it around, right? But this is like I mean, you never used this before, right? I've never used this before. But I hope you can understand like where it comes from. You just take the Bellman equation for V, right? This is part of that. And you sort of just expand out the value of the next state into this thing. It's just math. It's just very simple, right? So you can write Q in terms of Q, or Q in terms of V, V in terms of V, or V in terms of Q. This is just the interplay between Q and V. Oh, that makes sense. Okay. Any questions? That was, I think, decently heavy, especially if I just flash the math equations, but I hope you guys can see the intuition. When there's randomness, you account for how likely each outcome is going to happen, whether it's the policy, the transition dynamics, or the policy at the next state, right? If something isn't certain, you just have to weight that outcome by how likely that thing is going to happen. Okay. Now we're going to talk about optimal policies and optimal value functions. Optimal policy. An optimal policy, I mean, this is all fancy, a little like definition stuff. But intuitively, an optimal policy is better than or equal to another policy if the expected return is greater than or equal to that other policy in all the states, right? So if a policy is better than another policy, its value V at every state will be greater than the value V at every state between these policies. Because remember, the value V depends on the policy, right? So it changes for every policy. Yeah. An optimal policy is just the best policy. Okay. It's better than or equal to every other policy. Okay. So there's possibly more than one optimal policy. Okay. We'll see that soon. And the notation from now on, star, if there's a star, that denotes optimal. So pi star, V star, Q star. Pi star is the optimal policy, V star is the optimal value function, Q star is the optimal state action value function. Okay. And just this, I mean, sort of conceptualize it. So let's say this is the value, right? And let's say the x-axis are the states. In here, you can't really tell, you can't say for sure whether policy 2 or policy 1 is better. Because for some states, right, let's say this state here, policy 1 has a higher value, whereas policy 2 has a lower value, and vice versa in here. But here is sort of a demarcation between all the three policies. You can clearly tell that for every state, pi star is greater than pi 1 is greater than pi 2, right? I mean, very clear here. And something to notice and here is actually for some of the states, like pi 1 and pi 2 are equally good. So this sort of leads into the idea of there having multiple optimal policy, right? If in some state, one action and the other like have the same state action value or are like very good, then yeah. So I hope this is clear what an optimal policy is. And optimal value functions are simply like the value functions of the optimal policies, right? So all optimal policies will share the same optimal state action value function and the state value function. I hope this makes sense. It's just the best, it's just the value function for the best policy, whether it's V or Q. Does that make sense to everyone? Any questions here? No, right? Okay. Here's a fact. Kind of a weird segue, but the maximum, and you'll see why this is relevant later. I hope this is clear. The maximum of a set of real numbers is always greater than or equal to the average of a set of real numbers. Sounds good? Okay, moving on. Now, why don't I just do that randomly? Okay. Let's go back to the previous example, if you recall this environment, okay? Now, let's say that so if you remember the values here before were like, what, 40, 20, 10, okay? Let's assume this is the value function for the optimal policy, okay? And so there's a, this is the optimal policy in this state. And the optimal policy is stochastic here, which now that I think about it, doesn't make much sense in a finite state space. But let's assume this is the case, okay? Normally, yeah. So these are the optimal values, and you want to find the optimal value for this state. In other words, what is the best value we get for this state? So what do we need to consider, right? If you recall, previously, we had to account for, you had to average over the actions for the current state, right? Yeah, right? You have to multiply by 0.4 and 0.6, right? But I wonder, do we need to do that right now? Because if you think about it, you have the value here, which will be calculated in some way, right? 80 times 0.25 plus 50 times 0.75 times the discount plus the reward. That's the value of this action, like, going forward. And you have the value in this action. If you average these two things, that will be a smaller number than if you just take this number by itself. So what do I mean by that? So let's recall the state action value Bellman equation, right? This was one of the forms of it. I hope you guys can remember that, right? Can you guys see that? Yeah, okay. So let's consider the Q values for each action, right? Let's get the Q value of A1. What is the Q value of A1? It's 5, once again, just applying this equation. 5 plus 0.9, blah, 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 56.75, right? And the value the Q value of A2 in this is -10 plus 0.5, 0.9 times 90 equals 71. Doesn't make sense, right? It's just once again applying the Bellman equation. So we want the V star in this state, right? So let me ask you, do we care about the action that leads to a worse outcome, right? Do we need to average like we did before? Because if we were trying to find the Bellman, like the V, not the V star, just the regular V, if you recall the Bellman equation for V, you had a summation over the policy, right? So I have to multiply this value by 0.4 and this value by 0.6. But notice that we don't need to, right? Because we want the action that leads to the best outcome. We don't need now, so that means we don't need any more randomness in the starting state. We only consider the best action. So actually, the optimal value of this state, you don't need to average, just take the maximum. This is why I had that slide before about the maximum versus the average. Because if you had taken the average, then you would have been decreasing this value, right? 71, right? So that means that you just take the maximum. I hope that makes sense. This is the Bellman equation for V. Now there's something else. It's called the Bellman optimality equation for V star. We can simply replace, right, V pi with V star here, right? So this becomes pi star for the optimal policy and V star for the next actions. And like I said before, we no longer care about the randomness in the starting state because we only care about the best action. We don't care about the other action, right? So we just take the max. We take the max of this thing behind you, right? This thing here. Does that make sense? Yeah.
Yeah, but so over here we also need the V star of the subsequent.
Yes.
Right?
Yes. Yeah.
Oh, it is there.
Yeah, it is here. Yeah. Any other questions? Okay. Now let's once again do it for Q. This is the relation for Q, right? Do we need to average the next state actions, right? Do we need to consider the worst case state action pairs for the next states? No, right? So what we can do now here is take the reward, right? Plus 0.9, right? Discount times the dynamics, right? You have a random dynamics. But instead of averaging by the policy, you just take the maximum, right? Because once again, averaging is less than the max. So if you average 2 and 4, that will be less than 4. So you just take 4 and 7, right? I didn't write it out here, but you take 4 and 7 and multiply it by the probabilities, right? You care about the best possible value for this action. You don't care about the average anymore. You want the best possible. That's why you take the max, not the average. Once again, this is the Bellman equation for Q. And here you notice we got rid of the randomness in the next state actions. We took the best possible action over the next state. Is that clear to everyone? Yeah. Sure.
Thought you consider like you compared Q, obviously you take the maximum.
Yeah.
From Q, but you need to consider the two fractions. Like compare those.
The two, like you mean 0.25 and 0. No, because this is like part of the environment. So we pick the right action. Want to focus on the right action. You take the right action. This is like the underlying property of the environment, right? So, okay, so let's work this out. So the maximum value here is 4, right? The maximum value here is 7. But there's only a 25% chance you go here. And there's a 75% chance you go here. So you have to consider that, right? You can control what your value is. You can't control the environment. You can't control like, okay, I want to go to 7 100% of the time. You don't modify the environment you're working with. You don't go change the wind. You don't go to the moon and change the topography of the moon, right? The environment is something you cannot, this is randomness you cannot exclude. Does that make sense? Okay, yeah.
So given that we want to think of this as a dynamic programming problem,
Mhm.
we keep sort of traversing through the states.
Yes.
What would the end state look like, which base for our base case? How do we get the start for that?
You'll see that. You'll see that. I hope, yeah. Okay, Bellman optimality. Okay. Now here's a question I think maybe many of you didn't think about. How do you get an optimal policy from optimal value? Because as I said, right, there's three types of reinforcement learning agents. You have the policy-based method, right? Because at the end of the day, right, we want an optimal policy, a thing that tells the agent what to do, right? I said there's a policy-based method, so you can kind of see how that works, right? You sort of have a policy already, optimal policy. You have a policy and a value function, right? You train with both. So you can also see, okay, there's a policy in there. But what about value-based methods? Right? How do you, like, if you think about, like, if you get an optimal value, like, how does that help? That doesn't translate to a policy. So you have to think about that. But luckily, you kind of already saw an example of this, right? Let's go from the optimal state value function to the optimal policy. I said before, stochastic policy doesn't really make sense, right? Like, imagine you're in a finite environment. There should be one action that is like sort of better than the rest, right? It doesn't make sense that, oh, sometimes this is the best, sometimes this is the best, right? So actually, there is a best action here. So let's once again go back here, right? The value of this branch is 56.75. The value of this branch is 71. Right? I won't go over the calculations again. I hope it's clear by now. And you can directly see, okay, then obviously you just go to A2, right? You don't care about A1 anymore, right? A2 has the better value. There we go, right? So I hope this provides a bit of a hint as to how you would do it. Let's take the grid. I don't know if you guys remember this from last week, the grid world example, right? Remember, the reward is -1 per time step, except at A and B, in which case you always jump to A prime with reward 10, you always jump to B prime with reward 5. And the transitions are deterministic, no more randomness. If you go left, you go left. If you go up, you go up. If you hit a wall, you bounce right back. Recall, right? If you hit a wall, you bounce right back. Right? There's no more randomness. It's not like you go down, you might jump to this state. If you go down, you always go down, right? And there are 4 actions, up, down, left, right. Okay. Let's say we want the optimal policy for this state here. And let's assume this is the optimal value function. All right, it's given to you. It's given to you by some oracle. This is the optimal. How would you do it? Oh, sorry, just repeat slide. Sorry about that. Let's consider the up action. All right. Recall the Bellman equation. Do I have it? No, I don't have it. Okay, just recall. Rewards are 0 per time step unless you bump into a wall. So remember, okay, the up action, there's no more randomness in the policy. You've specified the up action, so you don't consider the policy. There's no randomness in the transition, unlike our previous example where you had like 25% chance, 75% chance. This time you go up, you'll definitely go up, right? So there's no more multiplying by all that random stuff. You take the reward, 0, plus the value of the next state, 0.17.5, multiplied by the discount factor. So you get that the Q value of this current state and the up action is 14. Does everyone see that? Right, once again, no more randomness, okay? This is an environment with no random environments, like wind or anything. You go right. Remember, when you go right, you get a reward of -1, you hit a wall, and you bounce right back. So this is kind of like the circular stuff you were talking about. You just sort of apply like your own value to yourself. So it's -1 plus 0.9 times 16, which is your own value. So it's actually 13.4. What is this? This is, once again, the Q value of the state and the right action. Going down is the same, 0 plus 0.9 times 14.4. I hope this is clear. I'll go through this faster. And going left is 0 plus 0.9 times 17.8. Makes sense, right? Okay. So what is the best action, right? You had 16. Okay, well, I'll tell you here. So it's going left. This is the optimal policy in this state. You just sort of compare which number is the biggest, take the biggest one. Because remember, these numbers summarize all future returns, right? And you just pick the biggest one. You don't have to think about anything else. Does that make sense to everyone? Yeah, okay. Well, you're really jumping ahead here. Yes, that will be for next week. I just have to explain a bit more about that, but yeah, a little bit. It's similar. And this, yeah, go ahead.
B 0 plus 0.9 times 70.
See, that's where you got the V and Q confused. This is the value function V. That was the Q function for the left action, or whatever. What'd you say? Like,
so I think the Q function for going from 16 to 17.8 itself should be 0 plus 0.4. it works out at 16 again. And then
Yeah, but this is the Q value for that action. Yeah,
because I think we start and
Yeah.
batch for that is 16.
yes, the optimal V for that is 16. Uh-huh.
Oh, okay.
It's the Q value for that. It's not the, yeah. Yeah, okay. So the optimal, so the corresponding action for this is the left state. I mean, that makes sense, right? Like if you think about this environment and where you want to be, you want to go left, right? You want to go towards A and B, these better states. So what you can do, you can just repeat the process I just did at every single sort of grid here, and you get that this is the optimal policy. Now, these arrows are just a result of doing that process. You compare the Q value of every single action in that state, in each state. Does that make sense to everyone? What just happened here? And I mean, you can see here, right? There's more than one optimal policy here, right? Because in certain states, you can go up and right. It makes no difference, right? So yeah, that's why I say like there's more than one optimal policy. Okay, moving on. I hope this makes sense. And once again, the math comes back, right? We have to do this. How do you get from the optimal value function V to the optimal policy pi star? You take the argmax. What's the difference between max and argmax? Max is the actual maximum value. Argmax is the thing that caused that maximum value. So the max would be the maximum value. The argmax, so you want the action that caused that maximum value. That is the optimal action in this state. Now notice in the example above, we didn't have any randomness in the environment, right? Because as I said again and again, you go up, you definitely go up. But in our own example, you had to consider a little bit of the randomness, right? Here, 0.25 and 0.75, right? To calculate the value for the Q value for A1. Does that make sense? There's randomness here, but in the grid world, there was no randomness, right? Because going up meant going up. They didn't mean going anywhere else. Kind of, yeah. The transition dynamics is always one, is always deterministic. Does that make sense? Right, because here, if you had went right, there's 100% chance you'll bounce back to this state. For this case, yeah. But for the case I just showed you, taking A1, you had a 25% chance of going here and a 75% chance of going here. But here, if you go right, you'll definitely end up back here. Okay. Sorry, guys. I think we'll have a break. I hope that's okay. I have too many things to go over. All right, so this is the optimal policy of all states, and this is the equation, which accounts for the randomness. All right, but in our situation, we don't have any randomness. What about getting the optimal policy from Q? I made it seem all mysterious, and it's like next week later. But actually, if you notice this part of the equation, right? If you recall, this is actually just the Bellman equation for Q, right? So actually, pi star from Q is just argmax of Q star. No more randomness in environment, right? Because it assumes like it encapsulates all of that. So this is the Bellman equation of Q. If you recall the equation, if you have the slides pulled up, you can go back. So this ties into why the Q function is much more useful. Because to get an optimal policy from the Q function, you don't need the environment. Whereas to get an optimal policy from the value function, you need the P, S prime, R, SA. Now, I'll just go over it briefly now. More of this will happen next week. All right, so it's okay if you don't get it, but just think about it for a minute, right? This is Q, and the environment term disappears. So, okay. And imagine like in how many cases in the real world, we don't actually know the environment. We actually don't know the wind. We don't know the dynamics on the moon. That is why the Q function is so much more powerful than the value function. But anyway. Okay, let's get to this. This is finding the value function. A lot of questions have been asked about, okay, you have this magical value function that tells you how good this policy is infinitely, like infinite time into the future. Everything. How do you actually find it? Right? I keep saying it's given to you, it's given to you. But no, I mean, there's definitely a way of finding it. The process of finding the state value function V, given a policy, remember, once again, I'll repeat this again, it depends on the policy. So for a different policy, you have a different value function. The process of finding this value function is called policy evaluation. Whenever I say this term in the future, policy evaluation, this is what I'm referring to. Okay, so for this case, the value function for the uniform random policy in this environment is this thing here. Notice how the numbers are much smaller than the optimal policy for this environment I showed earlier, right? Because it's not optimal. Okay. So now we'll go to an algorithm called iterative policy evaluation. And yeah, as the name implies, we'll be doing policy evaluation, but like repeating it. And what does this algorithm do? Well, given a policy pi and an arbitrary initial value estimate, we find the value function for that policy. So all this algorithm does is I give you a policy and an environment and all the other stuff like discount factor, whatever. You find the value function of this. Because previously I keep saying like you're given the value function of this policy, but this is the way you actually find it. And all this is you continuously apply the Bellman equation over and over again. So what does that look like? Let me tell you now. What will happen is you start with an initial value estimate. It's going to be pretty bad, right? It's not going to be the actual value function for this policy. But as you continually apply the Bellman equation, you'll eventually reach the actual value function. And this is, I think, for like finite Markov decision processes, this is guaranteed to converge. It will always work. Wait, I don't know, like tabular something. For something finite, this will converge. If you're working with infinite dimensional state spaces and neural networks and all that, maybe not. But yeah, for our cases, this will always converge. So this is what it happens. Eventually, you'll reach the value. Okay, you start with the initial estimate and you reach the value. All right. Okay, I've danced around enough. Let's get to it. Let's try this grid roll. Okay. There are terminal states in the gray squares. Okay, where you get a reward of 0. Okay, terminal states. The actions are up, down, left, and right, and the agent cannot move off the grid. So like if you go right in state 7, you end up back in state 7. The reward is -1 per time step every time you transition. So you want to get to the terminal state as fast as possible, either one. The discount factor is 1, so not 0.9, 1. And once again, the transitions are deterministic. There's no randomness in the transitions, okay? If you go up in state 7, you'll definitely go to state 3 100% of the time. You won't go to state 2, 6, 10, 14. You'll definitely go to state 3. So this simplifies it every time, okay? A lot. And what we want through iterative policy evaluation is the value function for this specific policy, for this random policy. How do we do that? So we start with the initial value estimate, right? You ask, how do we know, right? Where do we start? We start with all zeros. This is a common starting choice. We start with all zeros. Now, obviously, this is not the value function for this policy, but we need to start somewhere. What happens? Let's take this state, right? You want to update the value for this state. You apply the Bellman equation. What does that mean? All right, you go left, right? Once again, right? The randomness is in the policy, so you multiply this by 0.25, right? The reward is -1 per time step, remember? The discount factor is 1, so you don't need to multiply by 0.9 or anything. And the value of this next state, which we can be sure of since it's a terminal state. So you asked, how do we know the value? We have terminal states that we're sure of the value is 0. Okay, now we go down. We do the same thing. Right now notice this 0 is not this, it's like a different 0, right? This 0 we're sure of is the value of this state, but this 0 is our estimate of the value, right? So it's actually not the true value of this state for this policy, but we do the Bellman equation on it anyway. And once again, I'm gonna sort of go faster and faster through the Bellman equations because I hope you're just getting, right? You weight by the randomness of the policy 0.25, right? Going right is the same thing. Right, and going up in the same thing. And once again, to answer a circular thing, going up lands you back in this state. It's another circular thing. And this, in fact, this circular thing is even worse because this 0 is not the actual value for this state. It's an estimate, but you do it regardless. You sort of, doesn't matter for the cycle, you do it regardless. All right. And you update the value of this state once you, add everything up here, it's -1, right? So you update your estimate for the value of this state to be -1. Now, this is once again, not the same. Okay, so once again, there's a repeat slide. Sorry about that. So once again, this is not the value estimate. Rather, this is not the true value of this state. It's just an estimate. But we work with that. We work with what we have for now. Now you repeat for all the other states. So now for this state, it's also -1, and you calculate it the same way. But notice here that when you're calculating the value of the next state for the left action in this state, right? So here, you use 0, use the previous estimate. You don't use this estimate. You don't use the estimate you just got. You have to go through every single state first, okay? Using the previous state estimate. You don't use your newly updated estimate right away. Does this make sense to everyone? So now only after this is the first iteration done. One iteration is updating every single state in the state space. Make sense? So this is now the new value estimate. Okay, then yeah, so this is exactly what I just said. You copy over your new value estimate. So now this V prime is your next value estimate for the next time step. This is kind of confusing because I use V prime to denote the next state value, but here prime means at the next time step. Okay, so at k = 1, this is the value estimate. And you repeat. So you take this state, right? But now you can see the values are starting to become more and more different. So for this state, you do the same thing. Once again, it's a random policy. So you do 0.25, you multiply, the reward is -1. And then, but the next values here, notice, are updated, right? You use -1 here instead. For this state, right? So this state has a slightly higher value than this state, right? -1.75, -2. Why? Because this state is next to the terminal state. So the value here is 0 instead of -1. So it's a bit better. And this intuitively makes sense, right? If you're closer to the good state, the value should be a bit higher. That makes sense to everyone? Okay, and then so continuing this calculation, at k = 2, you end up with this value estimate. Or you can start to see it taking shape a little bit, the value estimate. At k = 3, you repeat the same thing. You apply the Bellman equation again and again. You get this estimate. You repeat, and eventually at k = infinity, this is the actual value function for the uniform random policy in this environment, given the given the necessary givens like the discount factor, the determinism of the dynamics, everything. Okay, so this is the actual value function. It's not like, oh, this is an estimate. If you take this process to infinity, this is the actual value function. Now, in practice, you don't go to infinity, right? You go to maybe 100, 1,000 time step. When it's good enough, you just stop. Okay. And once again, this value function sort of reflects. Yeah, go ahead. So yeah, so terminal states are special states in the environment that you want to go to. Yeah, that are good, right? So in this environment, you get a reward of -1 per time step, right? So you want to get to the terminal state here, right? So it's user defined. Maybe if you're on a moon mission, the terminal state is the lunar base, right? That is the place you know the value of. Notice that in all these infinite iterations, the value of the terminal state is 0 because you know the value. That is the actual value of the terminal state. Yeah, you had a question? Yeah.
So, said that the value function V is the expectation of the returns.
Yes.
From that state.
Yes.
How do we interpret the negative values here? Is it like how far are we from the?
No. So this no. So this is the value function of the random policy. So even if you're in this state right next to the terminal state, you can just go here, you can move away. So there's no notion of how far away you are from the terminal state if it's a random policy. If this were the optimal policy, on the other hand, the value of this state will be -1. Then you can think of it as a notion of distance because the optimal policy seeks the terminal state right away, right? So this is -1 away from the. Like because it's a random policy, you don't know where it'll go. It may never actually get to the. I mean, it will. If it's infinite, it will. But it may take a really long time until it gets to the terminal state.
And so over here, if we had some positive values for V, what would that mean?
You wouldn't. You wouldn't, right? Because the reward is -1 per time step. You would never have a positive value, right? The most positive value you'll get is 0. I hope that makes sense, right? Yeah. Because once you're at 0, you're out of the environment. You're no longer accumulating a -1 reward per time step, right? That's why the value is 0. remember, the value of a policy is the expected total future reward you'll get. Once you're at the terminal state, you're done. There's no more reward to get, so it's 0. Whereas if you're so in this state, it means that if you go like infinitely into the future, like whatever, however many times, you'll get an average of -14 for your return. And this makes sense, right? The uniform random policy is pretty terrible for this environment. It will be moving around randomly. It will eventually find an optimal, like it will go to the terminal state, but it will take a long time to do so. Yeah. It could, so you bring up a good point. For episodic environments, it can be 1. For infinite horizon environments, it cannot be 1. Because an episodic environment, I didn't go over that. That's a nuance I didn't think, but it's great that you thought of that. There are 2 types of situations in the real world. Things that end and things that don't end. In this environment, for example, things end. There's a terminal state, you go there, it's over. In a chess game, it ends. You want to go to a reinforcement learning agent for a chess game, the chess game will end, right? If you want to go to a lunar base, it will end, or you crash, or whatever. The episode terminates. But let's say you're trying to manage like a nuclear power plant that needs to be on 365 days of the year, 24/7 to provide power for a whole country. The episode never terminates. There's no, unless you're counting like maintenance breaks, but that doesn't count. Like the episode never ends. It's always on. You need to balance the needs of the people always. In that case, the discount factor cannot be 1 because then the rewards or the returns will be infinite. You need to, in that case, you need to do 0.9 or something. But in this case, because the episode terminates, you can have 1 for discount factor and remain finite. Does that make sense? So I didn't go into that because I didn't think it was necessary, but it's good that you pointed that out. Very good. So, I mean, this is exciting, right? You've just learned a method of actually getting the magical value function that I've been talking about, right? So yeah, that's pretty cool. And this is iterative policy evaluation. Once again, it's finding the value function for a particular policy in a given environment and given whatever discount factor, whatever. Now let's talk about something even more cool, policy iteration. Recall this is, okay, so this is how we got the optimal policy from the optimal value function, right? We sort of acted greedily with respect to the optimal value function, right? We picked the action that has the maximum Q value. That's called acting greedily. If you recall from the first lecture, you act greedily, meaning you pick the best value. Now, this is with respect to V star, the value, or the optimal value. But what happens, but we don't have V star usually, right? If you had V star, okay, this is easy. This problem is easy. You just act greedily. But we don't have V star most of the time. We only have V, like some value estimate, right? Like here, right? We only have this, the value for a random policy. So what if we applied the same logic? We acted greedily with respect to some arbitrary value function instead, right? So this is sort of spelling that out. What happens instead of acting greedily with respect to the optimal value function, right? Taking the best action, we did it with some arbitrary value function, right? Previously, if we do it with the optimal value function, the result is the optimal policy. But clearly, the result is not the optimal policy here. So what is the result, right? If you act greedily with respect to some random value function, the result is not the optimal policy. So recall, this is the the value function we just calculated for this grid world. And let's just apply what we learned, right? Like this is apply this equation, what we just did, to this environment now, right? Let's take this state. Once again, recall rewards are -1 per time step, okay? And discount factor is 1, deterministic transitions. So you can see how simple the Bellman equation becomes if you just sort of remove all the randomness, all that BS, right? So here, I think you guys are pretty familiar now. The Q value of the up action is -1 minus 20, right? No discount factor, or discount factor is 1. The right action is this, the down action is this, and the left action is this. I won't go over it. I think you guys are familiar with it by now. So clearly here, the best action is down, right? So let's just pick the down action for this, right? We're applying this equation to some arbitrary value function. What will happen is instead of having a uniform random policy, we obtain a new policy. Okay, this is the new policy we obtain if we just like repeat this procedure for every single square, right? Now, what you'll notice about this new policy is that, first of all, just to make sure that, it makes sense, right? We said the best action here is down, and it, in fact, is down. You'll notice that this policy is actually the optimal policy for this environment. However, this is sort of a special case. This isn't always the case. So it just so happens that this new policy is the optimal policy. But in most cases, if you act greedily with respect to the current value function, you'll end up with a policy that is a strict improvement over the policy you started with, aka the policy you used to calculate the value function with. Does that make sense? Right? It's intuitive, right? You found the value function for the current policy, and you act greedily. You select only the best actions in that policy. Of course, you'll end up with a better policy than the last one. But notice now, though, that this value function, or rather the value function for this policy, this new policy, is no longer this thing in the back, right? It's no longer -14, whatever. It's a mismatch. And as I said before, if you take this policy, the value function would probably be 1, right? Because in this state, right, the value function is -1 now. Sorry, not 1, -1 now. Because you go down with 100% chance. There's no longer a random policy. You go down with 100% probability, so the value is -1. Does that make sense? So what you end up having is that you improve the policy, but now your value function estimate is mismatched. It's no longer the same. It's no longer the value function for your current policy estimate. And this is just sort of the policy improvement theorem. It's like a mathematical thing, basically saying you can always obtain a strictly better policy by acting greedily with respect to the value function of the current policy, unless the current policies are optimal. Once again, like with pretty much all like reinforcement learning, like these things, a lot of them, it's guaranteed to work in like finite in grid worlds and stuff. But when it comes to like higher dimensional, like 17-dimensional infinite, like state spaces, it's a little, who knows. But this improvement theorem will motivate a lot of the decisions you'll see later on for more complex RL algorithms, basically acting greedily with respect to the current value function to get a better policy. This is a very common thing. I won't go into it in this course because it's beyond the scope. But if you do like look into the future and there's like policy gradient methods and stuff, you'll notice they sort of update the parameters of the policy to be greedy with respect to the parameters of the Q function. Okay, so it sort of mimics acting greedily in the continuous infinite state space situation. So now you might be thinking, okay, I just said just now, right? If you have a policy, you can find its value function through evaluation, and then you improve it, you get a new policy by acting greedily. But as I said, the value function for this new policy is no longer the old estimate you had. So what if you just do this again, right? You find the value function again, and you act greedily again. What would happen? All right. We arrive at an algorithm called policy iteration. And actually, recall what I just said, right? You start with a policy, you find its value function, you act greedily with respect to this value function, you get a policy pi2 that is definitely better than pi1. You find the value function again, and then you act greedily again, you get pi3 that is much better than pi2, and you realize if you repeat this a lot of times, you'll actually get to the optimal policy. This is true. This is a well-tested, true algorithm. So this is how you get an optimal policy. And I think that's pretty cool because, this is what we want in reinforcement learning. Yeah. If you act greedily with respect to the current value function, you'll get a better policy, right? And then you can find the value function of that policy, and you can act greedily with respect to that value function again to get a better policy. Yeah.
How many iterations in practical do we have to do?
It ranges. In the environment we just did, the simple environment, it took 1, right? Because if you remember, we acted greedily and it was already the optimal. But in other environments, we'll see, just like right now, maybe not. Maybe not. It might take a bit more. And this is just the diagram, right? You start with some arbitrary value. You evaluate, you start with some arbitrary policy and initial value estimate. You evaluate that policy, you get some V. You act greedily with respect to that policy, and you keep going until you get the optimal policy and the optimal value function. Once again, recall that the optimal value function is the same for every optimal policy. So, yeah. So that's why you see there like a point here, like the same thing. And this algorithm is called policy iteration. By the way, remember these terms like policy evaluation, policy improvement, okay, and policy iteration. I think it's pretty intuitive, right? Like you just sort of you basically it's like you're evaluating like a test or something for a student, right? You give them the value, right, and they improve based on that value, right? You give them test scores, they improve. You test them again, they improve again, right? Okay, let's tackle a more sort of complex example. Here you have a singular terminal state, this gray state. Once again, the actions are north, south, east, and west, or up, down, left, right. An agent can't move off the grid, so if you hit the wall, you bounce right back. The reward is -1 per time step, but if you go into a blue state, you get -10 reward. So think of it as like a wall, right? The discount factor is 1, and you have deterministic transitions. So once again, if you go up, you'll go up. Okay. And you want to find an optimal policy, but once again, we start with some random policy or some arbitrary. It doesn't have to be a random policy, but it makes sense to start that way. You can start with any policy really, but we start with the random policy. You can sort of already see like what the optimal value function is here, right? You go right, up, left, and there. So we got to go from the random policy to this. So we take the random policy and we evaluate it. Now, this is the evaluation. This is the value function of the random policy. And I didn't include the steps here, but it's literally just doing what we have done already. You look at the Bellman equation. You apply the Bellman equation over and over again until you get this. Okay. And yeah, I mean, it's a random policy, right? So the numbers are really bad, -200, right? Because, if you imagine the random policy might transition between these like walls a lot, right? But now what we can do is we improve the policy. We act greedily with respect to this value function using the procedure we just went through. And we act greedily, right? So after in one iteration of that, we see that, okay, the policy is like, it sort of makes a bit more sense, right? You can see that if you're here, right, you go up, you go left here, but it still doesn't make too much sense because you can see in the bottom row here, you're still sort of going to the left, which isn't the optimal. Also, if you're in this wall here, right, the best policy probably would be to get out of that wall, to go down, but here it's still going to the left, right? And why isn't it perfect? Why isn't the first step just perfect? Well, because the original estimate is, also it's for the random policy, right? So it's not like it's not good enough, right? So this isn't the optimal policy. And you'll notice now that the value function on the back here is mismatched. This is no longer the value function of this new policy we have obtained. So we evaluate the improved policy again. We take this policy, we evaluate it. And now you'll see that, okay, this is the value function of the much improved policy. And you can already see how much improvement there is, right? You go from -200 and something to like -2. You repeat. You evaluate the new, okay, sorry. You improve the, you evaluate this policy, right? And then you improve the policy. So this should say improvement and I think evaluation or something. Yeah. Actually, no. So I skipped a step. So you improve a policy, you reach this policy. This is a new policy. So these two policies are different, you'll see. So this is the policy you get after you improve this policy. And this value function is the value function you get after you evaluate this improved policy. Okay. And then you take this policy and value function, or excuse me, you take this policy and you improve it again. So if you notice from this policy, right, you have the things going down here. But now you'll notice that in the walls, the policy is learning to get out of the walls. And down here, it's a little bit more like random. Like before, it only went left, but now it's learning to it's learning that going up is equally important to going left. Okay, now, and in the new, even more improved policy, you'll notice that this state has actually corrected itself. It's going right now, but this state still needs some work, and so does this state. So you can see it's an iterative process. You evaluate the new policy, you improve, you evaluate again, and you improve. And once again, we keep doing it, and you'll notice the policy is starting to get better and better. You can see here, it's actually starting to go right now, except that in this state, it's still going through the wall. And you repeat. So I don't know how many iterations it is, maybe a bit more, like 10 more or something. Eventually, and this is guaranteed to happen, you'll obtain the optimal policy. Yeah. Is that clear to everyone, this procedure? Okay. Okay, I think, okay, so I guess we'll finish before 9 today. I thought this would take longer, but I think you guys got it so fast, so that's good. Yeah, so everything we've done here is dynamic programming. Okay, in a sense that for every state, we look at, so for each state, we look at its next states, and we update the value estimate or Q estimate or whatever based on that. And this is a summary of that. All right, let's say you have this, let's say this whole tree represents like all the possible outcomes you can reach in this state, ST, right? So you can go here, you can go to this state, and then from this state you take it action, you go here and you reach the terminal state. Here you go to this state. So this would be like a transition probability, right? Because after you take this action, you can go to one of two states. So there's some randomness there. So you can go to this state and then you can go to this terminal state. But if you mess up, you can go here. You can take this action instead, and then you go like, this is just represents all the possible outcomes. What dynamic programming methods do is they take this state, consider every single sort of possible next state you can get to from this state, and use that to update the value for the current state. So this like red triangle is meant to symbolize like how, like what you use. Again, like where, like how wide and how far do you look to sort of update your value, right? Once again, this is some intuition as to what the algorithm is doing. And next week, there will be a nice sort of comparison chart, same diagram, but with different methods, where you'll see that unlike dynamic programming methods, some methods maybe don't have this red triangle. They take one path to the end and look back. Or some methods just go one step. They just look at this tiny portion here. So this is meant as setup for next week when you see all the methods. But with dynamic programming, you have to look at every single sort of next stage. One step, yeah.
Over here, we don't have the idea of exploration, foundation. In order to looking at one thing and so hoping that leads us to the highest support.
Okay. So in dynamic programming, I think the concept of exploration and exploitation is a bit more sort of muddled. It's not as clear. In a sense, I mean, starting with our like random policy, I guess, is akin to exploring a little bit, because if you start with a random policy for each state, you have to consider every action and the values associated with it. Like if you have like if you don't start with a random policy and let's say for this state, you start with a policy that is like going up, I guess it can still work, because once again, this method is going to work. You only like the state value of this will only be updated like, based on the value of this state. It might take longer to converge though, because you see less of like the other states. Do you see what I'm saying? It will still work. It's not like it won't converge or break. But yeah, the concept of exploration and exploitation is a much more muddled in this sense. Because for dynamic programming, you're going through every single state. So you see everything.
Like every possible thing up, down, left, right.
No, because if you are, like I said, right, if instead of starting with a random policy here, you start with one action per state, deterministic policy, the Bellman equation term will no longer have like 0.25 times, it just be whatever it is, like -1 plus gamma, like it will just have one term. So you can still do policy evaluation, find the value function, and you can still improve that policy. Do you get what I'm saying? It might take a bit longer. I'm actually not sure. I think it will take longer. But in dynamic programming, notice in every single example, we have to go through every single state and do the Bellman equation for everything. And let me ask you actually, since you brought it up, is that feasible always? No, right? If you have an infinite dimensional state space, how you cannot use dynamic programming? Because there's infinitely many states to go through, infinitely many Q values, infinitely many Q values, infinitely many state values. That is where, when you cannot visit every single state, exploration and exploitation comes into play. You have to explore enough of the infinite state space to understand, like, okay, what is the value here? What is the value there? We'll cover this next week with Monte Carlo methods or temporal difference learning, but I might not cover the first one if we don't have time. So yeah. So I mean, I'm basically done, but I just want to do a recap because I think it's important. There was a lot of information this week. Very important. If you so you have to remember this. The Q function is how good a state in action is. It's like the V function, but it's for every state in action. So it encapsulates all future rewards. Here's the Bellman equation. Imagine if I showed this slide before all the examples. That's what I used to do. So I think you guys are happy that I went through the examples. Okay, hopefully I did a better job. But these are the Bellman equations. And once again, the math works out. You can do the math, but I like to think of it intuitively. For the value function, the value of the current state is equal to the reward you get plus the values of the next states, right? But of course, there's randomness. You have to account for the randomness of the environment and the randomness of the policy. Same with the Q function. You already picked the action. You assume you're already taking this action, so there's no randomness there. But you still have to account for the randomness of the environment and the randomness of the next state Q functions. Here's the Bellman optimality equation, meaning that once again, you don't care anymore about the randomness. You just want the best action. Deterministically, you want the best action. So for the value, you replace it with a max here. For the Q, you replace it with a max of the next state. If these concepts aren't like clear, go through this. For those that arrive late, go through the slides. I hope those examples make sense. Optimal policy is how to get them, right? You have to remember what an optimal policy is. It's a policy that has a better value than another in every single state, better than or equal to. And how do you get an optimal policy using the value function? V star is this equation here, right? You sort of check each action's Q value and you pick the best action for that state. Policy evaluation is the act of finding the value function of every policy. Okay. And the way we do that, I guess I didn't include a recap slide for that. The way we do that using dynamic programming is iterative policy evaluation. You go through each state and you continuously apply the Bellman equation. Eventually, I think definitely for tabular states and actions, it will converge to the actual true value. Policy improvement is you improve a policy by acting greedily with respect to the value function of the current policy. This will give you a new policy that is strictly better than the last one. But yeah, then once again, you have to find a new policy for that, or new value function for that. And policy iteration is, I think, our first proper, RL algorithm, where you initialize a random policy, you find the value function for that random policy, you improve that random policy using, greedy selection, and then you find the new value function for that improved policy, repeat. Eventually, it will take you from some like rubbish policy to the optimal policy. And also, as a side bonus, you get the optimal value function as well. Actually, let me ask you this. When do you know to terminate this algorithm policy iteration?
Budgets.
Yeah, when does that happen? When do you know it has converged?
So, like, us, like, even if you move
Right. If the value function no longer changes after improve the policy, you reach the optimal policy. Right? Because once again, reminder, the value function and the optimal policy are the same. Oh no. Okay, no, that was no. The optimal policy has the same like optimal value function. Okay. So yeah. Okay. We finished 15 minutes early. I'll be here until 9, maybe a bit. Please fill in only, I think one person filled in the feedback form. I guess I did that good of a job. Maybe that's good enough feedback by itself. And yeah, fill in the feedback form. If you have any questions, I'll be here. Please check out the UTMIST link tree for other events and workshops like this one, which are very helpful. And yeah, thanks for coming, everyone. Once again, I know next week is gonna be probably busy for you guys, I think, but I would strongly recommend you guys come because why is that? Because dynamic programming, as I just said, is kind of it's kind of like it's good, but it's kind of limited. You know, the state space has to be finite. There's another big issue that I haven't talked about, which I'll talk about next week. But yeah, dynamic programming methods are kind of limited. Okay, it's rare that you actually get to use them. But I introduce it to introduce Bellman equations and everything to you guys. Next week we'll be ending and going over we'll be ending on like a actual RL algorithm that you can actually use in real life. Maybe you guys have heard of it. It's called Q learning. Probably, maybe that word has been floated around somewhere in the ether. So yeah, please do come next week. It's probably one of the most important weeks. Yeah, please don't do the college lecture thing where like people stop them. Thanks.